So, let us start the new module, that is module number 6, and today is lecture number 1. In this lecture, I will discuss about the AC/DC load flow, or it is also known as a power flow. There is no difference between the load flow and the power flow. In some books they call it as a power flow, and some books they call it load flow. Basically, this term came because we wanted to know what is the power flow in the individual lines, branches. So, that is why the power flow name basically came. So, to start this, we have to see why we are going for the load flow, because this is the AC/DC load flow. So, first we will see the AC load flow, then we will see how we can incorporate. So, the AC load flow only I will go for the review aspect. I will not go much in detail, but slightly I will discuss what is this AC load flow, how it is done, what are the various methods, and what are the comparison, etc. Then I will move to the DC load flow. The question arises, why load flow? Basically, the load flow is required for the various applications as the planning stage, at your operational stage as well, and sometimes after the post contingency or post outage, etc., for the analysis purpose. In the planning, basically we know that suppose you are having a power station to be constructed at some place, then you should know what should be the transmission lines, what will be the capacity, what will be the voltage level, so that you can evacuate power from the generating station, especially you have to transmit it to the load center. So, we know that what will be the power flow in the different branches, existing line. If you are going to construct a new lines, then what will be the power flow pattern of whole system, what will be the losses, and at the same time you also require to know what are the various compensating devices are needed. The compensating devices I discussed in the very first lecture and first and two lectures, that we require the capacitors to improve the voltage profile of the power factor. We require reactors to control the over voltages during the off peak hours. So, all these things basically at the planning stage we require that, although in the planning stage there are set guidelines. For example, suppose you want to install a existing system, you want to install a power plant at any individual location. Now, that location also decided by several other studies. Once it is decided that you want to put at particular near to certain location, then you have to connect that generating station to the grid with the help of transmission lines. Now, there are some thumb rules that is applied or adopted in the various countries for the different voltage levels. Suppose you have this much x megawatt, then what will be the voltage level and how many transmission lines you are going to have. Always, for example, let us suppose here a generating station, it is decided that it will be here, and you have a network here, that is your complete network having all AC, DC and having generators, load, etc. So, here what we do normally, we connect here with the two parallel lines. Again, you know the two, because we want to give the reliability. We never want that this should be, suppose there is some problem in one of the lines, suppose only one line is there, we do not want to stop the generating station, because huge cost is involved here. So, if there is one problem, then another line can be taken, and normally these parallel lines are used. So, there are some thumb rules. Also, what should be the voltage level? It decided what is the power level of this. Depending on the power level, we know the surge impedance loading of the lines, etc. So, the voltage levels are decided by this power, how much power, that is not only one unit, there are so many units at that power plant. So, the total capacity of this power plant, then that decides the voltage level, and then accordingly we should have that generating transformer here, and then we can evacuate and we can feed the power here. So, this is very simple, because these are basically based on the thumb rules. You know how much power you are just feeding in the grid. Now, in the grid, it is a complex network. This power is going to be injected here, because we require more power here. Once you require the power here, now the question is how the redistribution of the power is going to take place here, and then what will be the, because earlier it was also loaded, now some of the lines will be overloaded, maybe some voltage may be going underloaded, lower limit or upper limit depending upon the system criteria. So, we require certain new additions of the lines. We can go to various compensating device like reactors, capacitors, etc., and then we have to go for complete, that is these planning studies. Then you require the load flows. Another basically we require for the online operation of the system. Normally, you have a power system right now, you know what are the voltage in the system. How will you know? We have the remote terminal units at the various locations. We get the information and we know what are the voltage at the various buses in the system sitting in your dispatch center. you know there is a various hierarchy where normally power system operates. Here basically at the national level we have the grid. This is the connectional, that is called national level. Then we are having the various regions here, that is called the, like we are in the NRPG, Northern Regional Power Grid, and southern, western and eastern, non-eastern 5 regions we are having. Here we are having in this various states in that northern region. Here I can say we are having UPPCL, UP Power Corporation Limited, we are having Rajasthan, we have Haryana, Punjab, Srinagar, Himachal, all these are basically interconnected. So, this is here we have the dispatch here, here. In this also we are having the various, again the area load dispatch, because it is a very big state. So, we are having, that is called the area load, ALDC dispatch centers normally are there, like we have in Panki, Moradabad, Mughalsarai, and one more somewhere we are having. So, even though that is not sufficient, here in this system we are having in each ALDC we are having maybe a generating station. So, this station is having its own control, the power plant control we call. Here they are controlling the load. After that, this power corporation is looking all this here all together. This NRPG is looking here and also its own generating stations if they are having, now it is a complex one here, and finally whole national grid is operated. So, in the operation all these persons who are sitting here, normally they are going for the load generation balance. They should know what are the voltage, what are the various frequency in the system. Based on that they can go for the load generation balance. So, one option that sitting here in the whole system we are having the remote terminal units, means at each substations is having equipped with the monitoring device like CTs and PTs are there. That information is going to here, and the person sitting here he can see what is the power generated by generating units, what is the load taken by various here the feeders, and also what is the power flow voltage at the various node, that can be here through the state estimators. Now, the question arises, we will come back here, what is the state estimation. So, that voltage present voltage is known through the measurement, it is not through the calculation. But the person who is here, he can see whether his system is secure or not, he can predict some contingency may occur, because right now if your system is okay, you are very happy, but there may be some outage of one of the line, your system may go somewhere else and your system may be collapse. So, what happens, the person sitting here, he tries to monitor the security of the system, means he can just predict if this frequency this contingency is going to take place, then what will be the scenario. Then what he will do, he has to run the load flow, because right now that condition is not there. So, he has to just calculate the load flow based on the current loading etc., and then he has to know what will be the voltage at various buses, what will be the power flow. So, the load flow here also required for the online operation of the system. We go for the contingency analysis, means various outages etc., then we go for see the security of the system, whether your system is present system is secure or normal or not, and then that is called, it is a normal operation also require your load flow. You should also require this load flow for running the various things, like if you require your stability analysis. So, for the stability analysis, the first step is the load flow, because you know what is the current state, then from there what is if some fault is occurring. So, in the present online operation we require the stability analysis, then we require the load flow, we require your security analysis, we require load flow. So, as I said, in the operational issues also we require the load flow. Another is the post disturbance analysis, we require the load flow, because something has happened, you have the complete information, load etc., then you can analyze the load flow and you can see what are the causes, what were the problems, your contingency has occurred. So, this load flow required for the all the 3 stages, planning, operational and the post analysis of the system, that is required. Now, then question arises, what is load flow? Load flow, as said in the beginning, the word the load flow seems that there is some flow and we are talking about the power flow or load flow in the lines. But the load flow basically what we do, we want to calculate the state of the power system. States are those minimum set of informations that is required to know all the other information from that. So, that is why you can say in the load flow what we do, we normally calculate the voltage and angle. You know the network topology. Topology means you know the connectivity of the lines, transformers, generators, etc. Then you know its parameters, means R, X and your charging etc. if there, you know the reactor value, you know the capacitor value, all the parameter we call the topology of the system is known to you, means we are having the admittance matrix of the network. It is normally known as Y bus. So, here this is the Y bus you are having, this is given to you. Then we require this V and angle based on what is your PGs, generations, what is your demand, what is your reactive power demand etc. Then we can calculate this in the load flow. So, we try to get the states based on the available information, this available informations whatever the system information, that is load, that is varying, these are the varying quantities, this is a fixed quantity. Based on that we calculate voltage and angle, and once you are having the voltage and angle, then you can calculate all the information, like you can calculate your reactive power generation, you can calculate the line flows, both real and reactive line flows in this. You can also get, of course, you are getting the voltages at all the nodes. You can calculate this P loss and the Q loss of the system. So, all these things you can calculate. You can also calculate the slack bus power. If loss is there, then slack bus power here you can also calculate. So, all the information which is required, you know, this and this information is known as the operating state of the system, because the voltage is keep on changing depending on your load, the power flow is also changing, and you should know, because these should not violate your limit. So, these are the operating states, so that we can get loss etc. we can get, again we should design especially that is required in the planning stage. We want to minimize the losses, we want to design our system that can give you a minimum loss. In operating state also, by changing the reactive power injection we can minimize the losses, that can be also done online, that is even though that we can also go for the cost minimization based on the scheduling of the generators, that is you are again online and using your load flow. So, now here I am saying that it can be calculated. I used another word here is called state estimation. Here this is state estimation. Now, you know the difference in the estimation and the calculation. The calculation basically the number of equations and your number of unknowns are equal, then you can calculate it. Means this is a simple calculation solving the algebraic equation. In estimation what is happening, you have a lot of data, in that you are estimating your again the state of the power system, because whatever you are having the data, that is measured data, they are having the errors etc. Based on that we can using large number of equations, we are trying to minimize the error that is measured and transmitted to your control center. So, the difference between the state estimation, here also we are estimating the state, that is a voltage and angle, here we are doing the power flow, here this is a calculation I am calling, here there I am calling the state estimation. The only difference is this. So, here we are just calculating voltage and angle, and thereby we are calculating all the information of the system. So, this is you done. Now, if you write the power balance equation at the various node, again since it is review, so I am not going to derive those equations, but if you remember here we write the Pi at real power injection at any bus, here that is it is your PGI, that is the power generation at that bus, and here I can say minus your demand at that bus will be equal to your summation of here Vi, the magnitude I am writing here, and it is your Gij cos delta Ij plus your Bij sin delta Ij, here your J 1 to n. This is the real power balance equation we call, and here you can say in terms of magnitude of voltage at bus I, bus J, and the Gi and the Bij are the elements of here, that is your of this bus matrix plus here J Bij. So, this is the Y bus elements, basically the real and imaginary component of this. Similarly, we can write here Qi, it is I can write Qgi minus QDI. Here summation of j is equal to 1 to n. N is the number of buses in the system. Here Vi Vj, here Gij sin delta ij minus Bij cos delta ij. Basically, delta ij is nothing but delta I minus delta j. So, here these are the power balance equations. This is a real power, this is a reactive power, and we are having the two equations at each node, because we are having n bus system. So, now our total equations we are having 2n in number. But if you will see, that is why the question arises, our number of variables are more. Our variables are 1, 2, 3, 4, 5, 6. Huh? This V is only 1, because we require the voltage, this, and we require the delta. So, we are having the 6 n variables, means at each bus we require voltage, we require P, real power generation, reactive power generation. So, 1, 2, 3, 4 voltage and the delta, means 6 variables are there. So, we cannot solve it. So, that is why we go for the classification of buses. Means we believe and we assume this demand is known at all the buses in the system, means load is normally measured and it is solvable. So, what happens from this? Now, we have reached up to 4n. So, now the 4n we have here, you can see the 4n, it is nothing but your Pg I at this bus, Qgi, Vi and the delta I. So, we have the 4 variables, we have the 2 equations at each node in the system. So, the total we are having 2n equations, we are having the 4n variables. So, what we do now, we have to specify, we have to set the 2 values and then only we can get the 2 values, and that is why the classification starts. So, in the system we defined that one bus should be a reference bus from where we can angle can be relatively it is changing. So, that is called your slack bus, or sometimes it is called reference bus, where we fix the voltage and your angle. So, these are basically your known values, this is a fix. So, we want to calculate here what will be your Pgi and your Qgi. So, this is your unknown. So, the slack bus is normally only one in a system, where this is the fixed, it is given to you, and then we calculate the real and reactive power generation at that bus, and it is called your slack bus or reference bus. Another is called your PQ bus. First I should start PQ bus, or it is also called the load bus, where your the PGs and your QGI are set, are given to you.
First one is slack bus.
Slack bus or reference bus, it is also given. So, again you cannot say this is the first, this is second, this is we are classifying basically. So, we classify the buses in terms of 3 buses, one is a PB bus, one is a PQ bus, another is slack bus. So, I said this is the first, so it is this value. So, now here in this classification we assume that the load buses are those buses where generation, real and reactive power are known. Once they are known, now the left out is your Vi and delta I, means this is unknown and we should calculate. Third one, we know it is a PV bus, or also it is called generation bus, where this Pg is known and the voltage is known. Then we go for Qgi and your delta I is calculated. Why at the PV bus we fix this? You know the Pg is the real power, it is set by the turbine. How much steam you are flowing through the turbine, which you can control. The reason is there because we can control the Pgi there, although you can set this value. The voltage you can also set because you have the exciter, and from the excitation you can control the Vi, but these things are depending upon the network and how much it is connected. So, the voltage here Q is basically the Vi, and the network information will set your reactive power generation at that bus. So, these basically 3 buses are classified. Now, we are to fix to known, so we can solve this power flow equation.
So which one is the infinite bus?
Infinite bus is a different concept at all, where we believe your voltage and your frequency does not change of the system, that is known as the this one. For example, infinite bus, what we say, let's suppose you are having a generator. Here you are connecting with the system, this is called infinite bus. Here the voltage and angle we said is 0, and whatever the power you are injecting here in the system, the frequency and the voltage of the system does not change. So that is called infinite. Although there is no infinite bus practically, but a very strong grid can be treated, or big bus can be treated as an infinite bus. This analysis normally used in your stability analysis, because we can equivalent whole your system as infinite bus, and this generator behavior we can analyze it. So especially this is used in the stability analysis. So this is something different than this. Here we are fixing, we are not worrying about the frequency, we are assuming the frequency of the whole system is same, and here the voltage and angle are this we are setting. Infinite also I said here V angle 0. 0 you can put, or you can put any value. So this is also sort of reference bus, but it is not that is treated in that sense which I am talking here. Now you can see these two equations are highly nonlinear, because you can see that you are having here the cosine and sine terms. If you expand, you are having the large number of terms, and it is highly nonlinear, I can say. So again you have to go for the certain methods, because this is you are having the set of equations at each node, and you are having the set of unknowns, then you can solve. Again you require the various techniques to solve these nonlinear equations. Now the question arises, as you know, this is a nonlinear equations. Any nonlinear equation will have large number of solutions. If it is a quadratic equation, it will have 2. If it is a cubic equation, then you are having 3, and so on and so forth. Now what will be the number of solutions for this? And also for solving this, if you are having higher order numbers, you require some initial guess. So starting with the initial guess, you can solve this, and you can have a large number of solutions. Here also you can get large number of solutions. And for example, why I am telling this, you know this equation here, 2x plus 1 is equal to 0. Here the solution, it looks only x is equal to 1, but it is not so, because the two equations are coinciding, two solutions are coinciding each other. Means here x1 and your x2 is equal to 1. But if you are changing here something 3, you are having both different here, x1 and x2, means effectively you are having the two solutions, but at certain point they are going to converge, and there is having only one solution. If you remember your PV bus, here as I said the PV curve, if two bus system you are having, just remember the two bus, here you are having a generator, here this is one bus, and here we are having a load. This is a two bus system. If you draw this here, the voltage profile by the power which you are taking, the voltage here it will be keep on changing. So this is a system having two bus. Now you can see, if it is two bus, you are having the two solutions. For any given P, you are having the two voltages. But once you are coming here, you are getting here at this point only one voltage. So here also you are having the multiple solutions, but if the system loading keep on increasing, you can some of the solutions are coinciding each other, and finally you are having only one solution, and after that there is no solution. You cannot have solution at all. So beyond this, it is called unsolvable condition, means you cannot solve even though this nonlinear equation. But if you are inside here, there is a possibility, since here the solutions are here going to one point, you cannot get the converse solution. Solution is existing, but you cannot get the solution. So that is called divergence of solution or unconvergence of the solution. So you should mind it, there is a difference between the unsolvable case and the solvable with the not getting solution. Means beyond this point there is no solution, but here solution exists, but you are not getting it. Based on it, again different methods may give, some methods may not give. So that is called divergence of the solution. Here is an unsolvable case. You cannot solve it, means there is no solution exists at all, because you will see sometimes in Newton-Raphson the Jacobian basically becomes singular. Now, here once I want to tell you here, you can see this relation. Normally the solution here, the number of solutions that exist for this is approximately here 2 to the power n minus 1. For the 2 bus system, here the 2 solutions. Similarly, you are having n number of solutions. Another thing I want to tell you, we are least concerned about this solution, because your system is operating near to unity band. It's 1 per unit approximately. So that is why we start our initial guess is called the flat start. 1 0 we start, because we want, if you are starting with the very some absurd voltage here, you may get the solution here, which is not of our concern. Sometimes it is required, those are analyzing the voltage instability and other analysis. So that solution may also required, but in the normal operating people, they are only concerned about this solution, because this is the real practical solution, that is our operating condition which is existing here. So that is why here we require the initial guess here one angle normally 0, that is called flat start. Because if you are starting here 1, you will end up here before this. So the flat start is called, and thus we go for the initial guess this. Now, so this is a nonlinear equation. We are just going to get a large number of solutions, and this should be solved by the iterative procedures, or we can have some approximation and then finally we can get the solution. So now the question arises that here we can land up the what are the various methods of load flow. So now we are classification is over. Now let's go for the load flow. Now in the load flow, already since it is I am only reviewing, I am not going much in detail of the various methods, but the most commonly used methods you must be knowing, that is called Gauss-Seidel load flow method. You know, Gauss method itself is there. In Gauss-Seidel means you are Gauss method, then you are having Gauss-Seidel, then you are having Newton-Raphson load flow method, and then you are having FDLF, fast decoupled load flow. In between also some people say decoupled load flow, because in between this method derived from here to here via this decoupled load flow. Here in the NRLF we are having the 2 types. One is called the polar, another is called rectangular coordinate solutions. So it is, if you are writing the equations in polar, like if you are writing this equation here, then it is polar, and another is in your rectangular coordinate method. Now the Gauss method basically and the Gauss-Seidel method, there is no much difference, and these methods basically derived based on, why I am deleting this, because we are going to use for the Newton-Raphson, I will show you it. Another concern, just I want to, before going the method, we use this Y bus. Why not Z bus? You know it very well, because this Y bus is easily formed by looking, even though network you can form the Y bus, and also this bus no doubt is a complex matrix having real and imaginary, and it is highly sparse. So earlier people were facing the problem of the storage, because the memory were not so cheap and it was very complex to store. So sparsity techniques were used, and the matrix is highly sparse. You have to store very few elements. But if you are going for the Z bus, it is a full matrix, and that is why it is not sparse. So that is why in starting from beginning we started with the Y bus, and this load flow, all the load flow methods are now basically running on the Y bus methods. So we form the Y bus. There is a different approach out there. Whether you are connecting a line, whether you are connecting a transformer, your Y bus is keep on modifying, and then you can have the complete one. So there is a different techniques are there to form different ways, you can say, approaches. Now this Gauss method basically we again arrive from the very simple principle here. This is your SI conjugate will be nothing but your VI conjugate into your I. These are the complex power. Now this is equal to your Pi minus JQI. I am writing this power injection at ith bus. We can write in this form. Now this I here, it is this II, this here conjugate. I can write simply here your Yij into your Vj, here j is equal to 1 to n. From the Y bus, here it is just based on basically the nodal methods here. Here this is the admittance matrix, here you are this multiplying by j, and if you are adding you will get the I injection at that bus. Now, what happens here? This we can simplify. Here we can write this Vi square Yi plus here I can write, I think I can write the Vi here conjugate, we can just take at this, and then here j is equal to 1 to n, but not I. I can write here Yij, these are the here Vj. So, in the Gauss method what we do, we solve this equation by knowing P and Q, we try to determine the Vi and these values are known, means I can write from, again simplify here from this value, I can write here this Pi minus j Qi divided by your Vi conjugate 1 over this is the Yi, from here minus your summation of Yij Vj j is equal to 1 to n. So, if you are solving this equation, it is called Gauss-Seidel method, means you are calculating the voltage at all the PQ buses, you are calculating the angle of this voltage at all the PV buses. Knowing your P and Q at all the load buses you are knowing, at the PV buses you do not know this Q. So, what we do, from the initial guess whatever Q is there you put it there and you can calculate the angle, and it is an iterative process. So, here we just calculate Vk plus 1 minus Vk, that is all the buses should be less than certain epsilon, and then we say the solution is converged. We keep on solving, putting this value, because once you, first iteration you have taken the initial values, you are calculating all the Vi's, then you are again checking here, again putting this value and then calculating. This is the iterative process. In the Gauss-Seidel what we do, because in each iterations we are having some of the values calculated in the same iteration, and if you are utilizing that, then it is called Gauss-Seidel method. So, what we do here, we normally expand this with the known in the same iteration and unknown in the another iteration. So, here I can say j is equal to 1, here it is your I minus 1, because you know this, minus summation j is equal to I plus 1 to n, here your Yij Vj. So, what we do, if you want to calculate here k plus 1 of this, before you are calculating you are knowing this value, here it is a k plus 1 iteration value known to you, here you are using this already this just calculated this, means in the same iteration you are these values are known, because before I we are known, these voltages are known and remaining you do not know. So, this is called your Gauss-Seidel method. This method is very simple, no doubt, as you can see, but only the problem here, the convergence problem, because this is very highly nonlinear. If your system is highly loaded, system is very complex, this criteria is very difficult to get, and finally you cannot get the solution. So, that is called the divergence solution. Solution exists, but we are unable to solve by the given method. Here we use some acceleration factors to accelerate the speed, but still that sometimes it is not possible, then people go for your another method, that is called Newton-Raphson methods. You know the Newton-Raphson methods, it is based on the Taylor series expansion, and we take the first derivative terms remaining second order and others, we can just remove it, ignore it, and then we can solve. This is just like your function f(x), we want to solve is equal to 0, because this Pi minus this value just we are going to solve, and that's it utilize your Newton-Raphson method. So, now let us see in the Newton-Raphson method, it no doubt is based on the Taylor series expansion, and we form the Jacobian, and it is called, if the power injection here for corresponding to I am writing in the vector form, here this is your q, we take this is a Jacobian, that is the first derivative of this equation, means this is related to your del p del delta, del p del v, here del q by del delta, here del q over del v, and here we are having the change in angles and change in the voltage, and we calculate these values Jacobian, we can invert it here, these values are known to you, you can calculate the change in the voltage and angle. So, this is basically in the your polar coordinate. Normally here to make it a more faster convergence, what we do, instead of this we divide here v, here we multiply, no, here by v, here we do v, yeah.
No, downward.
This by this will be alternately multiplied. If you are doing the dv upon dv, it is same. So, basically this v is going to be multiplied here, that is correct. Now, what we do here, if you are differentiating here, we apply here to make this and this Jacobian quadratic, because if you are differentiating with the voltage, because in this equation you can say this is only quadratic. So, once you are differentiating with the voltage, you are having with the one term, and if you are multiplying with this, means you are having the same, because if you are differentiating with the delta, the sine becomes cosine and cosine becomes sine, and this is the voltage quadratic. So, to make it here, it was found it is a more convergent if you are using del b upon v, because this is also quadratic, this is already quadratic the terms in terms of vi, v square and the cosine and deltas, this is also, here we are doing this. So, this is your Newton-Raphson method in the polar coordinate. Here this q is basically done for only the load buses, this p we calculate for all the buses except slack bus, and then its order here decided by the number of your load buses. Because load buses here sometimes in the load flow, sometimes reactive power is hitting, we also have the reactive power limits of the generators. If they are violating, then from the PB it is converted to the PQ, and then again if it is not hitting, then it will be going back. So, this dimension of this matrix is very dynamic, but it is very powerful and it normally it is used, it can go up to any, and normally it converges in the 4 to 5 iterations only. If it is not converging in the 4 to 5 iteration, means it will not converge. So, it provides a quadratic convergence, it is very fast, it is very reliable, and it is widely used for the large power system as well. We have another one that we write this equation in the rectangular coordinate, means here what we do, we write the voltage at any bus, here I, it is magnitude Vi angle delta I we wrote. So, this is called in the polar coordinate representation. We can also have it is EI plus here JFI, means real component and the imaginary component, then it is called the rectangular coordinate. Then you can modify this equation accordingly. In that case, you can again here the modify this, and then it will be called the Newton-Raphson in your the polar coordinate, rectangular coordinate. Here instead of this, we go for here del F. Here this is changed, your change in del E, here del F, and here del F. In this case, the size of here is not equal. What we do, E and F we require at all the buses. So, what we do at the generation buses, the voltage is specified. So, we add some more equations because this is unsolvable. So, we require V square at the generation buses, EI square plus FI square. These equations are also added, and we add here, this is for load buses, this is for your change in Vi square, and we just go for 2 more elements here, del Vi square over del E, del Vi square over del F. We just add 2 so that it can a square matrix, and then you can invert it, you can calculate it here. This is Newton-Raphson method in the polar coordinate. In Newton-Raphson, it was found the polar coordinate the off diagonal elements. Now, I can remove this, and I will use del delta here del V upon V. It was found that this Jacobian and this Jacobian is very small. So, it was treated as 0, and then we can have the decoupled equations here. We can solve this is equal to this one directly, it is independent of this. Here this is only dependent on this. So, this is the decoupled equation. Then fast decoupled load flow came, we used this equation and we made certain assumptions that the sine delta here is equal to delta ij if it is in radian, the cosine delta is treated as 1, and the multiplication of this here with the delta here is very, very larger than this. So, we can do some approximation, and then based on that FDLF method came. So, fast decoupled method is also used for the various applications, even also for the load flow, and it has a various assumptions. Already you can read the books for more detail. So, from the decoupled, the fast decoupled came, and these are the basically Newton-Raphson and the fast decoupled load flow methods are very widely used for all your applications. So, this is the comparison between this. Now, I think we have to go for another one, that is the DC. Now, looking at this, we have to now go for the various DC power flow methods. There are basically the three type of DC power flow methods can be categorized methods. Here one is called your sequential method, another is called your unified method. The two method is widely known. In the sequential method, what happens? You can see it is AC and DC are solved separately. Means you have to solve this AC, then you have to solve the DC, because this P and Q at the DC bus are basically known. Based on that, you can calculate your DC variables. So, the AC and DC equations are solved separately in each iteration. Only you can see in the DC equations, AC variables are also there. If you remember here, if you are writing this VD R, your 3 under 3 EM you are having by pi cos alpha minus 3 XC upon pi ID. Here you are having, this is your AC voltage, the peak value, or you can just make it RMS value. So, this at that where it is converter is connected, you are having the AC voltage. So, what you are doing, you are solving this, that voltage is coming here, you are calculating the DC variables, you are solving the DC equations, these variables again you are just solving here and keep on, it is repeated. So, it is very easy, and earlier it was used, but nowadays it is not used, because here the convergence becomes very difficult, because sometimes it may be possible that you are getting the oscillating solution, means your convergence criteria does not meet. Your convergence criteria here, it is your change in P, it is so, should be less than epsilon value, and change in Q in epsilon value. Now, again here the question arises, since your fast decoupled method and the Newton-Raphson methods are based on the assumptions, so whether the solution is approximate solution or exact solution, to know this answer, you can see what is the solution. Solution means we want fx for any equation. If you are not having fx is equal to 0, if you are getting x by any approximation or any assumptions, this equation is satisfied for the given x, means this is the exact solution. So, in the Newton-Raphson and the fast decoupled methods, no doubt we are having lot of assumptions. In spite, our convergence criteria, we are making del P and your del Q are less than or equal to your epsilon, that is a very, very small. If it is 0, this is the exact solution. So, your solution correctness that is based on your, basically I can say, depending upon, is not based on your assumption, based on how much you are going to put your tolerance. If you are putting a high tolerance, means you are getting approximate solution. If you are putting it very tight, means equal to 0, you are getting the exact solution, because here this x is satisfying this equation. So, your whatever the criteria you are using, it is not required that one. We have to see the tolerance limit here. If you are putting very tight, it is called 0. If you are putting 0, it is very tight tolerance. If you are putting large value, it is very loose tolerance, and then your correctness or exactness of solution is defined. So, another is called here I was talking, it is called your unified method. In this unified method, it is as name, you are combining your AC and DC variables. In the sequence method, what we are doing, we are solving AC and DC separately. Here in unified, again the unified, this method is of two types. One is called your extended variable method, another is called variable elimination method. Means your unified approach here, we are having the extended variable method, and another is your called the variable elimination method. So, if you are here, the solution vector basically is extended with the DC variable. Here we are having P and Q, these are the AC variable. Now, if you are using some DC variables, equation corresponding to this, and if you are having here your variable that is x DC vector, then it is called extended, your Jacobian, you are extending it. We will see what is R, what is x DC, what is the DC variables, and then corresponding here the elements are, those are modified, means here we are adding del R over x. Oh, sorry. So, we have to go for this extended, means it is not only adding here, we have to see here del P x DC, del Q x DC. Here we are having del R, here it will be delta, del V y V, del R here x DC. And now, here we are having our del delta, del V upon V, and here change in x DC. So, this is called your extended variable method, because we are extending this AC with the DC equations and then we are solving in unified way, not sequential way. Another in unified way, that's I said the variable elimination method. What we do, we try to these equations here simplify in the such a fashion that these equations can be substituted in the P and Q itself equations, and then means the DC variables are eliminated, and then we can just solve here, means they are inside with the starting some value, and we can solve the voltage and angle, and from there we can calculate the x DC. It is called the variable elimination method, and we will see later on. So, if you are extending, it is called extended variable method. Here no doubt your Jacobian size is increased, the complexity in the programming are increased, because you are calculating some extra here the element, this element, here, here and here, you are calculating the 5 more Jacobians basically I can say, and they are corresponding to various elements. Sometimes it is very difficult, especially in the extended variable methods. Now, you can say your FDLF does not work here. In FDLF what we are doing, we are making this 0, but now if you are making 0, still they are related to each other. So, you cannot have the decoupled equation and you cannot solve the unified equation. But if you are having this variable elimination methods, you are having the same concept, and then you can even though try to apply that the fast decoupled method as well for the various applications. So, in the variable elimination methods, the FDLF can be included, but extended variable methods it is not possible. But again, both are very widely used, because if you are making here the elimination, you are making the complexity. Here it is very simply you are adding the few equations, the DC equations, and you are solving this Jacobian, very simple. So, this is your unified approach. So, in this elimination variable methods, what we do, the real and reactive power by the inverters we take as the voltage dependent loads. Then the DC equations are solved analytically, and the DC variables are eliminated from the power flow equations, because once you are taking load here, then DC variables are solved and this variable basically included. It is also a unified method, because the effect of the DC is included in the Jacobian, because this extended method here it is also unified, because here in this Jacobian you are including this one. So, already these variables are there. So, no DC voltage is included in the solution vector. Here the DC voltage we will see, we are not including in the this vector. What is the x DC we will see in the later one. So, the unified the variable method is advantageous, that it can be this reliable method, the FDLF can be developed. It is it can be very easily incorporated in both your already if you are having the this program code, you can very easily that put this value, that modified value here in the unified scheme. You can very easily modify it. Only you require, will see few elements will be changed, other will be not changed. Means out of this, if you are having two terminal network, only this element corresponding to this node and this node will be changed, other will be as it is. So in the unified, that is a variable extended method, it is very easily to incorporate here, only to modify the few elements. If you are going for extended variable method, you are using some more Jacobians, and then it is slightly complex. Here this is also very easy to handle the switching mode. Now you know the converter characteristic, remember it is keep on changing. If you remember the converter characteristic here, it is not straightforward here, it is your like this. So now we have to see where is the converter is operating. It's operating here or it is operating somewhere. So the mode is where you are here, you are here, you are here, or you are here. So the modes are basically keep on changing. So in this also you have to keep on changing your modes. We'll see again. Now it looks very complex, but once we'll analyze, it will be very simple. It is also used very easily for the, if you are using the unified scheme with the variable elimination, you can again solve your same stability, voltage stability criteria, and you can get it without any problem. Now here these are the 5 basic equations we are keep on deriving in the HVDC. You remember here, this is nothing but your the rectifier side voltage. This is, I can say, the rectifier. This is, you can take as R, you can take this is AR, because the tappings at both sides is changing. So R is representing your rectifier and your I is representing the inverter. So I can say here it is R, here is R, here I can say R. So we have your the tap changers here. One is to AR, that is online, as I said, the transformers are equipped with the online load OLTC here is having. This is your rectifier voltage, this is your AC terminal VTR voltage. So already we can write, now I am writing instead of EM here under root 2 term is appearing, so that we are writing the RMS value. So this is a terminal voltage, here you can see this is a simple, we were using this value. Now here the VTR, you can say the 3 under root 3 term is missing. This under root 3 term is missing because here we are taking in the per unit. If you are taking the per unit, again I will come later on that what is the base quantities, what will be the base power, because the AC base is the different. We are having some base quantity because load flow is solved in the per unit. So similarly we have to go for the DC side on the base. So from the AC side base we should have certain base for the DC. So in the general sense I can say the here the this WR here, it is the rectifier delay angle minus here the reactance, this drop. You have the inverter. This equation basically is related with this equation in the other end, because there is a line impedance, resistance is there, and the inverter, this equation is there. The PR and the DI we can calculate directly this one. This AC will come, I will discuss later on, but we are having the 5 basic equations. Out of these 5, only 3 are the independent, because these are basically derived here. So out of 5, the 3 are the independent equation, 1 to 3 are basically here the R equations, we will see later. And these are again the, here we can solve the nonlinear equations, and then we can incorporate in our either extended variable methods and the variable elimination methods that we will do in the next turn. So with this I will stop it here, and more the sequential method we will discuss on the next turn. Thank you.